So, you think you know coding? Well, today we're going to talk about a world where the rules are completely different. This isn't about your typical web app. This is about embedded systems, where your code isn't just running on a server, it's directly controlling physical hardware. And we're going to see why, in this world, coding standards aren't just about making things look neat. They're about controlling the laws of physics.
Let's just kick things off with this absolute truth of embedded engineering. You can have the most brilliant algorithm in the world, but it means nothing if the code itself can't be trusted to run the same way twice. The real monsters here are these silent, sneaky bugs that pop up because the C language itself has, well, let's call them gray areas. So our first job is to tame all that chaos. You see, the C language gives a compiler a shocking amount of creative freedom. And in the world of hardware, that freedom is just plain dangerous. We need our code to do exactly what we wrote every single time with zero surprises.
And here is the #1 villain, undefined behavior. Think of it like a blank check you hand to the compiler. When it sees code it doesn't have a strict rule for, it's allowed to do whatever it thinks is fastest or easiest. And you know what that might be? It might be deleting your code, reordering it, or just creating a result that makes absolutely no sense at all.
This right here is a perfect example. Look at the code on the left. It's trying to change the variable a twice in a single instruction. The C language standard never actually says which one should happen first. So, depending on your compiler, you could get a totally different answer. It's a gamble. Now look at the right. A coding standard says, nope, one change per instruction. One clear action, one guaranteed result. No chaos, no gambling. Now that unpredictability gets way, way scarier when you introduce something called an interrupt. In an embedded system, a physical event, like you pressing a button, can literally interrupt your main code at any time to run a special little function. If your main code and that interrupt routine are both trying to use the same variable, you get a race condition. It's a nightmare bug that might only show up 1 in a million times.
And here's how we fix it. Without that special word volatile, the compiler tries to be clever. It looks at the main code and thinks, hey, this flag variable never changes here, so to be faster, I'll just cache its value in a register and stop checking it. But then the interrupt happens. It changes the flag in memory, but the main code never sees it because it's looking at the old cached value. By adding volatile, we're telling the compiler, don't be clever. This thing can change it anytime. You must go and read it from memory every single time. Okay, I'm going to throw a number at you. 44. What in the world could 44 have to do with your code failing without you ever knowing it? Think about how we store numbers.
And there it is. A UNT-AT is an 8-bit piece of memory. It can only hold numbers from 0 to 255. So what happens when you try to cram the number 300 into that tiny box? Well, it overflows, wraps all the way back around, and what's left is 44. And the worst part? The compiler probably won't even warn you. This just happens. And a system controlling a motor or a medical device, that silent error could be catastrophic.
All right, so we've figured out how to rein in the compiler's weird habits. But now we have to face an even tougher boss, the real world. You know, the laws of physics. Our code doesn't just float in the cloud, it runs on actual silicon that has real limits, like time and memory.
In these kinds of systems, a correct answer that arrives too late is simply a wrong answer, period. Think about it, right? An airbag that deploys a second after the crash is totally useless. A motor controller that misses its update window can cause vibrations that literally shake the machine apart. Timing isn't just a nice to have, it's a fundamental part of being correct.
And this is how we manage time. The code on the left is a trap. It just waits for that flag to change. What if it never does? The program is stuck there forever. It's a black hole. You can't predict how long it will take. But the code on the right, it's predictable. It will try for a set number of times, and if the flag doesn't change, it moves on anyway. It guarantees an exit. That allows us to calculate the absolute worst-case execution time, which is critical for proving a system is safe.
Now I know what you might be thinking. Okay, but come on, what's a few bytes of corrupted memory? My laptop has gigabytes of RAM. But on a tiny chip, with maybe a few kilobytes, what's the real damage? This is the damage. See, a tiny bit of memory corruption, like a Stack Overflow, rarely causes a crash right away. Instead, it quietly overwrites some other, seemingly unrelated piece of data. The system keeps chugging along, looking perfectly fine for hours, maybe even days. And then, at some random moment, the code goes to use that corrupted piece of data, and the whole thing just collapses for no apparent reason. Okay, so we've seen how to control the compiler and how to respect the physical world. Now, let's put it all together and talk about how we go from fragile code to genuinely bulletproof firmware. This is all about designing for safety right from the start. So here's a super common situation. A developer needs to wait for a piece of hardware to be ready. So they write this simple loop that just sits there checking a hardware register over and over until its value changes. Seems totally logical, right? But here comes our smart compiler again. It analyzes the code and says, nothing inside this software loop ever changes the reg variable. So obviously, it's always going to be 0. I can optimize this by just turning it into an infinite loop. The compiler is totally blind to the fact that the hardware itself, something outside the software, is supposed to change that value. And the solution, once again, is our friend volatile. We're basically giving the compiler a direct order. We're saying, listen up, this specific memory address is special. It can be changed by forces beyond your knowledge. You are forbidden from making any assumptions about it. Read its value fresh from memory every single time. Truly robust systems are also built in layers, kind of like a cake. Coding standards really encourage this. Your main application logic shouldn't be messing around with raw hardware registers. No way. Instead, it talks to a clean driver, which talks to a hardware abstraction layer. This separates everything out. If something goes wrong, the problem is contained to one layer, making it so much easier to find. Plus, it makes your code way more portable and easier to test. We've gone through a lot here, so let's bring it all home. In the world of embedded systems, coding standards are not about style. They're not a nice-to-have. They're a core engineering tool for building safe and reliable products.
And you know, one of the biggest wins is that standards make your code checkable by a machine. Special tools called static analyzers can scan your code and find entire classes of these sneaky bugs, like null pointers or race conditions, before you even try to run the code. It's like having a robot assistant who's an expert at finding these kinds of problems.
And for a lot of industries, this isn't just a good idea. It is the law. You want to sell a product with a computer in it that goes in a car, a hospital, or an airplane, you absolutely must prove that you followed standards like MISRA C or DO 178C. It's not optional. You can't get certified without it. And that really is the bottom line, isn't it? Without standards, you're not really engineering. You're just writing code and hoping for the best. You're gambling with how that physical hardware is going to behave. These rules are how you take control, remove chance from the equation, and guarantee that your code does what it's supposed to do, safely and predictably every single time.